This assessment asks us to predict a structure for this spectrum. Now, to go through every step of this process with everything I have on the board would probably be about a 15-minute video. So I've done a lot of the work ahead of time, and I'll talk you through how I got here. If you're unsure about anything I have on the board, I refer you back to this section of the textbook, or certainly talk to your instructor. The first thing we'll look at is the molecular formula. The molecular formula tells us that the index of hydrogen deficiency for this molecule is 0, which means no pi bonds and no rings. I've labeled each of the signals in this spectrum, and we should build puzzle pieces for each of those signals based on the chemical shift, the integration, and the multiplicity. For signal A, the chemical shift of 3.3 tells us that there are hydrogens on a carbon next to some kind of electronegative element, such as bromine. The integration is 2 hydrogen. These 2 hydrogens are the hydrogens causing signal A. I've gone ahead and underlined them here. I'll explain why in a minute. And the triplet tells us that there are 2 neighboring hydrogens on the carbon next door. So here's our neighboring carbon with 2 hydrogens. And the last thing I've done is have a box here to indicate that that carbon on the end still has 1 open valence. So when I go to build the structure, I'll need to include 1 more bond to that carbon. Signal B has a chemical shift of 1.8, has an integration of 2 hydrogen. Again, I've underlined these 2 hydrogens. And it's a quintet, meaning we have 4 neighbors. Can't have 4 neighbors on 1 carbon, so we'll split them up among 2 carbons, 2 hydrogens on each side, on the neighbors on each side. Those neighboring hydrogens are not underlined. And again, each of these 2 carbons has 1 more open valence, so I've shown that with a box. Signal C has a chemical shift of 1.5. It has an integration of 1H, so there's only 1 hydrogen on this carbon. I've gone ahead and underlined it. And it's a no-net, which means there are 8 neighbors. There's only one way to get 8 neighbors, and that would be 2 methyl groups on one side and a CH2 group on the other side. The CH2 group still has 1 more open valence, and so there's a box here. Signal D is a chemical shift of 1.3, an integration of 2 hydrogen, they're underlined, and it's a quartet, meaning we have 3 hydrogen neighbors. One way to do that is to have 2 hydrogen neighbors on one side and 1 hydrogen neighbor on the other side. Open valences are shown by the filled boxes. Finally, signal E has a chemical shift of 1.8, an integration of 6 hydrogens. Can't have 6 hydrogens around 1 carbon, so the next most likely scenario is 2 identical CH3 groups. And it's a doublet, so those are likely attached to a carbon that has 1 hydrogen neighbor. The neighbor is not underlined, and that carbon has 1 more open valence shown by the box. Now that we have the puzzle pieces for each of these signals, we can start to overlap those puzzle pieces to build our overall structure. I'd like to start with something that I know is going to be on the end of the molecule. I know methyl groups are going to be on the end of the molecule, so I'll start with signal E with those methyl groups, and I'll draw them over here. These methyl groups have 1 CH group as a neighbor. The signal E is 6 equivalent hydrogens next to 1 hydrogen neighbor. The way that works is I need to look for some other signal that represents 1 hydrogen with 6 hydrogen neighbors. If I have one signal that represents 1 hydrogen with 6 hydrogen neighbors, I can overlap that with signal E to start to build out the puzzle for this molecule. I can do that with signal C. Signal C has 1 underlined hydrogen, and it has 6 neighboring hydrogens. I'm looking for ways to overlap underlined hydrogens with non-underlined hydrogens between the puzzle pieces. That's how I build confidence that I'm building the right structure. If I overlap E with C, I have the underlined hydrogens, the 6 underlined hydrogens overlapping with the 6 non-underlined hydrogens in signal C, and the CH group from signal C overlapping with the CH group not underlined from signal E. That also brings along another CH2 group, so I can continue this analysis with signal D. Signal D has a CH2 group next to a CH group, so I can use that relationship to overlap signal D with signal C. The CH groups overlap, the CH2 groups overlap, and now I get 1 new CH2 group next to signal D. Here I have a CH2 group next to a CH2 group, so I'm looking for some other puzzle piece that has a CH2 group next to a CH2 group. That would be signal B. I can do that with signal B. The CH2 groups overlap, and I get 1 new CH2 group. The last puzzle piece to incorporate is signal A with the bromine. The CH2 groups overlap, and the bromine on the end fills out to the rest of the molecule. By laying it out like this, I can see how the puzzle pieces overlap to build the overall structure. The last thing to do is to add them all together, and so I end up with a final structure that has the 2 methyl groups attached to a CH group, which is attached to a CH2 group, which is attached to a CH2 group, and a CH2 group, and the bromine. Or I could draw this out in line angle form. And this would be my overall structure for this molecule. This is the structure that represents this spectrum.